Hi, everyone, and welcome to Introduction to Statistics. In this particular lesson, I'm just going to give you a primer as to why we study statistics, some basic concepts such as order of operations, and 8 emerging rules from the order of operations that will help you if you have to calculate statistics by hand. Then I'm going to do a quick demo on how to do that. But let me share my screen and we're going to get started. Let's start from the beginning. So you might ask yourself, well, why do we study statistics anyway? Well, the first thing I'm going to tell you is that we need to have a grasp of statistics in order to understand all of the professional journals that we read, because the professional journals that we read, they utilize statistics to draw the conclusions that they do. Now, obviously, if you're in a psychology statistics class, likely you're going to have experimental psychology as well, and you're going to have to read these journals and understand what they're saying. So if you don't understand what they're saying, then you're likely going to have to rely on other people's interpretations. And one of the problems with relying on other people's interpretations is sometimes people make mistakes. And if you don't have a grasp of statistics, you might miss the mistakes that they've made. So also a second reason is that you're going to be using statistics for your own research typically. So if you're a researcher, you need to understand the assumptions behind the test, the rules as to when we use a given statistical test, and that will help us apply it appropriately to our own work. So again, as I said, you have to understand the rationale behind behavioral sciences. When I teach experimental psychology, I spend a lot of time getting my students to really think about what their research question is and help them form operational definitions, which is a specific statement as to how something is either going to be measured or manipulated. And understanding that is crucial to being able to determine which statistic is appropriate for the study that you're doing. Sometimes, if the statistic is not appropriately applied, you can draw erroneous conclusions, and then that will create problems, especially if you publish and other people are going to want to challenge that work. They're not going to embrace it, right? So, and I did say you need to know statistics for your own work. Now, it's important to understand that if I were to draw a flow chart, right, and I were to say statistics, right, there would be descriptive statistics and inferential statistics. But, well, what are descriptive statistics? Well, descriptive statistics in general are summary scores, right? So when we talk about descriptive statistics, they summarize or describe the data. Things like percentage, right? Cumulative percentage, frequency, cumulative frequency, percentile rank, mean, median, mode, z-scores, things like that. These are all descriptive statistics. Now, what I will tell you is that the first half of psych stats is all about descriptive statistics. But if we want to draw meaningful conclusions about a population based on our sample, we need to know inferential statistics. So things like t-test, analysis of variance, correlations, regression, chi-square, all of these statistical analyses are inferential. And the purpose is to say, did we have statistically significant differences in our sample relative to what we would have expected by chance? And if so, we say that our study had an impact, right? Or there were significant differences or a significant relationship, depending on the test. But we need inferential statistics to draw those conclusions. Otherwise, we won't know if the numbers we have are meaningfully different from one another. So inferential statistics, you're drawing conclusions about the population from a sample. So you're making inferences, whereas descriptive statistics, you're summarizing your sample, but you're not making any meaningful conclusions. Now, I think it's important to dive a little bit deeper into the language I use. I said inferential statistics allow us to draw meaningful conclusions about a population from a sample. So what is a population? What is a sample? And what are the mathematical calculations that we use when we have one or the other? So a population by definition refers to all individuals of interest. A population is the whole entity, the whole group. Now, populations can be small or large. And I know when you think of population, you probably are thinking to like large scale data of like countries and population studies like that. But we as researchers get to define our population. So if I was interested in just the students in my psych stats class, well, then my population would be relatively small and I could gain access to all students in my class, right? I could collect data on all students in my class. If I extend that definition a little bit to all students in psych stats at the college, now the population has gotten bigger, right? So it's every single section of psych stats. It makes it a little harder for me to gain access to every person. And then of course, if I say all psych stats students in the nation, well, then it gets harder and harder. But why am I telling you this? I'm telling you this because in most cases, it is very hard to gain access to the whole population. So the vast majority of research you have is conducted on samples. Now, the mathematical computations that we use differs when we have a population versus a sample. Now, the sample is a subset of the population. So we are acknowledging that we don't have all of the individuals that are part of this whatever variable we're studying, but we have a sufficient number and we're hoping to have sufficient representativeness, right, within that sample. Now, the mathematics you use for a population when you have access to all parties or all individuals of interest are called parameters. So parameters are the mathematical computations we use for a population. When we're relying on a sample, we rely on statistics. And it's implicitly stated in the name of the course, right? We call this psych statistics, that we are already assuming that you're not going to have access to everyone you want to have access to. So statistics are the mathematical computations we use for a sample. Now, I'd like to give you a mnemonic to remember when we're using parameters, when we're using statistics. PPSS. So we use parameters in a population, we use statistics in a sample. The letters match. Now, right now, this may not mean much to you, but what I will tell you is that many formulas, when you're doing a computation for a sample, are more conservative. So the formula is slightly different when you have a sample relative to a population. And I think that's important to say now so that you can anticipate in later lessons that, the formula is going to be slightly different. All right. Now, we also talk about sampling techniques, and you might be familiar with the various sampling techniques from a research methods course or another course that you might have learned. But if I were, again, thinking through the lens of like flow charts, if at the top, we would call it sampling techniques. And then we have this concept called probability sampling versus non-probability sampling. Probability sampling refers to when you know the likelihood of an individual being selected as part of your study. That's crucial. If the likelihood of this individual being selected is known, we're operating based on probability sampling. Non-probability sampling is when you don't know the likelihood of an individual being selected. So obviously, when you want to generalize from the sample to the population, it helps to have probability sampling. So knowing the specific likelihood of this individual being selected allows for us to have better understanding about our sample and its representativeness. So when generalizability is very, very important to you, probability sampling is the gold standard. Now, non-probability sampling, you don't know the likelihood of an individual being selected, but that doesn't mean that it has no utility, right? If you are just trying to see if in your sample you have statistically significant differences, then you could draw meaningful conclusions about your research question in your sample, but you can be a little bit more cautious about generalizing to the population. So I guess what I'm trying to say is that it's not all or nothing. Even though you don't know the likelihood of an individual being selected, that doesn't mean it's useless entirely. It has value. And in fact, I'm going to tell you, most research studies operate in one of the subtypes of non-probability sampling. And I'm going to get there. So let's talk about the three common types of probability sampling. First, we have simple random sampling. And in simple random sampling, we know the likelihood of being selected, and every individual within that sample has equal probability of being selected. So that's very important. We know the likelihood of being selected, and every individual has equal likelihood of being selected. So that's simple random sampling. Now, in many research areas, we want to try and match or mirror the real world. And so there are ways to do this, right? So we have things like stratified random sampling, which would take the relative proportion of this subgroup in the population and match it in your sample. So if we had, I don't know, let's say 40% of the population was Caucasian or white, and I'm making it up, I'm not saying these are the actual numbers. Well, then we would want 40% of our sample to be white or Caucasian, right? So we're trying to match the ethnic group with the proportion in the population. But still, the reason why this is called probability sampling is because we still know the likelihood of being selected. So we put you in a strata based on whatever factor we're looking at, and we match you based on that composition, right? So this is very helpful in generalizability. But again, I keep saying that the likelihood of being selected is known because we're going to talk about another subtype that's very similar to this, but it's a non-probability technique. We also have cluster sampling. So now instead of taking an individual, right, as the previous two did, cluster sampling is if we take a group of people and all of its contents. And that has its value when you're trying to study perhaps differences within a group or within a cluster and how outcomes differ. So I'll give you an example of that. So stratified random sampling, here's an example. Let's say the population was made up of triangles and diamonds, right? And we had X number of triangles, X number of diamonds. Now, when we sample from triangles and diamonds, we want to make sure that the proportion of triangles are in our sample match the proportion of triangles in our population. And the same thing goes for the diamonds in our sample. We want to match it to the diamonds in the population. So cluster sampling. Suppose I wanted to study, I don't know, licensure exam outcomes. And what I wanted to do is I wanted to study across universities, right? So different universities, you know, they have different training models and whatnot. So let's say in cluster one, I selected City University of New York, CUNY Graduate Center, and cluster two was Rutgers, and cluster three was Teachers College, and cluster four was NYU, and so forth. Well, when I select City University of New York, now, because City University of New York was cluster one, I bring in all of its students and I look at their performance on the licensure exam. What about Rutgers? Rutgers was number two. Well, Rutgers wasn't selected, so I select none of its students. Then number three, which was randomly chosen, was Teachers College, right? So Teachers College, I would select all of its students and study their licensure exam outcomes. Four was NYU, right? I would study none of the students from NYU, and so forth. Now, this technique is beautiful because we can assume that there is a system for each of the universities, right? There's a system, and it's different across universities. Now, granted, all universities are, you know, bound by teaching at a minimum certain coursework and certain material, but how they teach it could be different. So that's what we talk about cluster sampling. So you can see the difference between cluster sampling and the other probability sampling is you take every individual that is part of that program rather than just individuals within themselves and not others. So non-probability sampling, the likelihood of being selected is an unknown, right? So the most common form is haphazard sampling. You might hear it referred to as convenience sampling. And in convenience sampling, you just take volunteers, whoever you can get. Now, I said to you that the most common way we do research is actually non-probability sampling. And in fact, most of it is this haphazard or convenience sampling. Now, purposive sampling, here is where you have prerequisites to be being selected. So you have to meet a certain criteria in order to be selected. But once you've met that basic eligibility requirement, it operates similar to haphazard sampling. Now, you may recall in the previous slides, we talked about stratified random sampling. Stratified random sampling, you try and match your sample with the proportion of the population. Well, quota sampling, you do the same thing. So in terms of approach, it's the same. So we're still trying to match the relative numerical composition of the subgroups with the population in our sample. However, the probability of being selected is an unknown with quota sampling. And that is the difference between stratified random sampling and quota sampling. So quota sampling uses a haphazard way, and haphazard, again, is just based on volunteer and not knowing the likelihood of being selected. Now, some disadvantages of haphazard sampling is it does introduce a potential bias, right? So not knowing the likelihood of being selected, you could have a selection bias or a volunteer bias. And we know that volunteers are different in many characteristics than non-volunteers in general. We also know that if we don't know the likelihood of being selected, we have to be very careful with our interpretations because the results of our sample may not generalize out to the population. Now, I said earlier that if that's not your goal to generalize to the population, and you're just looking for meaningful differences, then maybe it's fine, right? And then obviously one of the biggest criticisms is you don't put any restrictions on how people are selected in convenience sampling. Now, here is just a table, a summary. I'm not going to read off the slide. Again, each sampling technique has advantages and disadvantages. If simple random sampling was so easy, everybody would do it. So obviously it could be challenging to use probability sampling techniques, and that's why we go into non-probability techniques. Now, the next thing I want to teach you is about scales of measurement. And I'm going to do a series of mini videos on SPSS, and the scales of measurement are going to be important, right? And I think that it's important to talk here because when you have to code your variables, right? When you make your data file, you're going to need to know whether it's nominal, ordinal, interval, or ratio. Now I'm going to say it here and then I'm going to say it there, but interval and ratio data on SPSS is just referred to as scale data because they have equal units of measure. So let me go through it. Nominal scales of measurement are these differences are categorical or qualitative, or the differences are in name only. We don't believe that there is a better or worse outcome, greater than, less than outcome as it relates to these kind of variables. All we know is that it's more frequently occurring or less frequently occurring. So If we were looking at animals, right? So dogs, right? There are many different subspecies of dogs, right? What's better, a German Shepherd, a Rottweiler, a poodle? Well, it's kind of a silly question, right? They're just categorically different. And the same thing with other animal species, political party. Um, there's nothing objectively better about one political party over another. Now, I identify with a given political party, and I'm sure you do too. But that doesn't make that political party inherently better because we identify with it. What that means is that that political party, its value system is more consistent with our value system. And then other political parties, the reason why people endorse those political parties are based on the value systems that they have. But objectively better or worse, nah, nothing, right? Religious affiliation. Obviously, we have in the United States a Christian majority. So about 7 out of every 10 people in the United States is Christian. But that doesn't necessarily mean that Christians are inherently better than non-Christians, right? And the same thing for Jewish individuals, Muslim individuals, Sikh, Hindu, etc. It's just categorically different based on the theology. Gender, right? So if we're looking at gender, and I know gender is more complex than this, but males and females, transgender individuals, and so forth. Who's better? Well, that's silly, right? Now, in psychology, we know that there are more females relative to males in the classroom. But that just because they're more frequently occurring doesn't mean that they're better, right? Because if we went to a different major, we might see more males than females. And the argument would go the same way. Just because it's more frequently occurring doesn't mean it's better. So what's the point? When we look at nominal data, we're looking at categorical differences, categorical differences. And we can make meaningful conclusions, right? We're going to talk about chi-square later in the semester. But when we look at it, we're just looking at frequencies that we have in our sample relative to what we would have expected in our sample. And that's what nominal data is all about, right? So now let's shift to ordinal data. As soon as you get to ordinal data, now you can put things into rank order, better, worse, right? First, second, third place. So if you're talking about a swim meet, right? We know that the gold medal is better than a silver medal, and the silver medal is better than the bronze medal, right? But the biggest problem, right? So we can put you into rank order, but the biggest problem with ordinal data is it doesn't have equal units of measure. So if we were going to swimming, right? So how much faster was the gold medalist relative to the silver medalist? How many seconds or fractions of a second? And then from the silver medalist to the bronze medalist, how much faster was the silver medalist to the bronze medalist? The answer is that it's not always uniform, right? So between gold and silver could be, for example, I used to give this example when Michael Phelps was swimming, especially in Beijing. He would be like 3-4 full body lengths ahead of the silver medalists. And then the silver medalist to the bronze medalist would be a fraction of a second, right? So we're talking several seconds versus a fraction of a second. not equal units of measure. So ordinal data's biggest criticism is while we can put you into rank order, it does not have equal units of measure. Interval data, interval is where we now have equal units of measure. However, we don't have an absolute zero necessarily. So if you get a 0 on this measure, it's not an absolute 0. So let's talk about the weather, right? So if you were to live in the Northeast, you'll talk about sub-zero temperatures, right? So 0 degrees Fahrenheit and even 0 degrees Celsius is not an absolute 0, right? An absolute 0 would be when there's absence of heat or temperature. And that only happens when molecules stop moving. So when you watch the weather in November, December, January, February in the Northeast, it's not uncommon for you to hear them talk about sub-zero temperatures. It's 10 degrees below 0. Well, if 0 was an absolute 0, there should be nothing below it, right? So examples like temperature, another example related to it is psychology, right? So if I give you a psychological test on an IQ and you get a 0 on the IQ test, does that mean you lack intelligence altogether? No, of course not. Usually that means it was unmeasurable by the test, right? The floor was not sensitive to where your IQ was, and different IQ tests have different floors. So 0 is not an absolute 0. Now let's go to ratio. Ratio, you have an absolute 0. 0 is 0, right? So before you get on a scale, what does the scale say? 0.00 pounds, right? Or kilos. So when you get on the scale, it changes. But a pound or a kilo is an equal unit of measure, and the scale was calibrated to a 0 beforehand. So 0 is 0. If you take one of my quizzes and you get everything wrong, well, it's an absolute 0, right? So height, time, and so forth, all of these things are at equal units of measure and absolute 0. Now, you may remember the 4 scales of measurement with the mnemonic NOIR, N-O-I-R, which is a French word for black, but it's also the first letter of each of these words. All right. Now, the next piece is probably what you might have learned in algebra is the order of operations. The order of operations is absolutely essential in calculating statistics by hand, because most of the errors that people make when they calculate statistics is that they might have violated one of these rules, right? So in general, you might hear the mnemonic called PEMDAS, which is the same thing I did on the previous slide, which is take the first letter of each word and create an acronym. So PEMDAS stands for parenthesis, exponents, multiplication, division, addition, and subtraction. That's the order of operations. And you cannot skip a step, right? Because it will change the outcome. Now, when I was learning, we didn't call it PEMDAS. We actually had a whole sentence, please excuse my dear Aunt Sally, right? Which was our way of doing the same thing, but it's a lot easier to do it this way. All right. And you'll also see summation notation, right? So you might see in some statistics books, sigma that seemingly it looks like an E if you see my cursor. Sigma means to add, right? Right? N at the top is your end point, right? Because we talk about the N as your sample or your population number. I is your starting point, right? And then X is the score. So the sum of X, if you had the sum of X by itself, you would add all scores, right? But it is possible to have a starting point that isn't the first one and isn't the last one, right? So you can have a different starting point or end point. Now, in advanced statistics, we talk about trimming procedures and cutting off the tails a little bit. So you might have a different starting point and end point to what you're adding. But in general, I teach you this just in case you come across it. But in general, we're adding the whole column. Now, if you look at rules of summation, there are 8 rules of summation. And I'm going to go through this briefly, and then I'm going to go through it with a different kind of like manual calculation process, right? So there's the sum of X, right? When you see this first one in the top, the sum of X means that's the sum of the X column. The second one, you see the sum of X squared. That is the sum of the X square column. Now we have parentheses. Remember PEMDAS, right? So the sum of X in parentheses squared. So we sum the X column first, then square that number, right? And then as a function of this, we have 8 rules, right? And I'm going to read them and then I'm going to prove them if you don't mind. Rule 1 is the sum of X plus Y column is also equal to the sum of the X column plus the sum of the Y column, right? Rule 2 is the sum of X minus Y column is equal to the sum of the X column minus the sum of the Y column. And I encourage you to write what I'm saying down, because I'm actually tipping my hand with the way I'm reading the rules. So slow down this lecture as you need to, replay this lecture as you need to understand the rules. Then we have the sum of the XY column is not equal to the sum of the X column times the sum of the Y column, right? So in this first scenario, you multiply the X value by the Y value first, right? And then you add that column. In the other side of the equation, you add the X column first, add the Y column first, and then multiply that across. All right. Rule 4 is sum of X square column is not equal to sum of X squared. And then we're going to shift to other rules. Rule 5 is the sum of the K column is equal to N, which is the number of participants in your study times K, right? And K is a constant, right? Now, rule 6 is sum of the X plus K column is equal to the sum of the X column plus the sum of the K column, which is also equal to the sum of the X column plus N times K, which is basically an application of rule 5. And then rule 7 is the sum of the X minus K column is equal to the sum of the X column minus N times K. Last but not least, the sum of the K times X column is equal times K times the sum of X. And I'm gonna show that now. So let me stop my share and pause the recording, right? Because what I'd like to do now is go into an actual spreadsheet and prove these rules to be either equal or non-equivalent as we go. All right, so give me a second and I'm going to pull that up. Okay, so what I just did was I created a spread, basically a Word file that I haven't filled in yet. So we're going to do this together. And I'm going to show you how to do what these formulas or rules say. So now, not doing this yet, I'm just going to make up some numbers, right? So we're going to say 2, whoop, I don't want to underline, 2 and y, we're going to make 7. And we're going to go down, make this one 4, 3, then 1, 1. Now I'm intentionally making it a small sample because for the sake of this, I want to be able to work with you, and I don't want to have like really heavy mathematics to calculate. All right, so here are all our columns, right? So the first thing you're going to want to do is populate your column. So x plus y. So in this first one, I would be doing 2 plus 7, right? And that would equal 9. Now, I don't need the 2 plus 7 because I'm just showing you the process. So I'm going to put that 9 there. And then again, this would be 4 plus 3, which would equal 7. Again, just showing you my process. And then 1 plus 1 would equal 2, right? So now I've filled out that column. Now I need to get to the x minus y column, right? So here we have 2 minus 7. Whoop. 2 minus 7, which should equal -5, right? Now I'm going to delete the process. Now I actually am going to stop doing that because I can verbally say it and you'll follow along. 4 minus 3 gives me 1, and 1 minus 1 gives me 0. So that column has been done. X, Y, what we're doing here is we're multiplying, right? So again, just like these imply, this would imply 2 times 7, right? So whenever you see 2 letters next to each other, that typically means to multiply. So 2 times 7, what is that? That's going to be 14, right? And then we have 4 times 3, again, taking the x column and then the y column, we put them next to each other. 4 times 3 gives us 12. And then last but not least, 1 times 1, well, this is easy, right? 1 times 1 is 1. Now, we have one more column to do, and this is the x squared column. I could probably make this more easily understood to be x squared by doing font superscript. And so what is x squared? Well, 2 times 2 is 4. 4 times 4 is 16. 1 times 1 is 1. Okay, so now I'm going to add these columns up. And what I'm going to do is then apply these to the first 4 rules. So what is the sum of the x column? Well, what is 2 plus 4 plus 1? That is 7, right? What is 7 plus 3 plus 1? That's 11, right? What is 9 plus 7 plus 9, that's 18, right? What is negative 5 plus 1 plus 0? That's negative 4. What is 14 plus 12 plus 1? That's 27. And what is 4 plus 16 plus 1 is 21. Now, I basically just did some quick math. Again, this is the benefit of using a smaller data set. So in rule 1, we said that the sum of x plus y column, right? We added that column up, which came out to 18, was equal to the sum of x column, which was 7, plus the sum of the y column, which is 11. Now, if we were to continue to work through the math, we would want to prove this rule to be true. 18 is equal to 7 plus 11. Well, what's 7 plus 11? 18. So now I have taken the numbers above and proven rule 1. We're going to do the same thing for rule 2, right? So in rule 2, it says the sum of the x minus y column, which we got negative 4, is equal to the sum of x column, which was 7, minus 11. See, so sum of x column is what is here, right? And then the sum of the y column is what's here. So 7 minus 11, if we were to continue to prove this rule, would be negative 4 is equal to negative 4. Let me get rid of that typo, right? So I'm proving the rules based on the columns, right? So I'm taking one column versus another. Now here we have a rule that is a non-equivalent. So rule 3 says the sum of the x times y column is not equal to the sum of x times y, right? So let's start putting that together, right? So what rule, the sum of the xy column is 27, right? So we say 27, again, we want it to be a regular font, right? 27 is not equal to, insert symbol. All right, I need a not equal sign, so I have to go through the symbols. Okay. All right, I'm just gonna write is not equal to sum of x column, which is 7 times the sum of y column, which is 11, right? So let's continue to balance this equation. We're saying 27 is not equal to 77. Does that make sense? So we're just proving the rules based on the columns. Now, we also have rule number 4. Rule number 4 says the sum of x squared column, which is 21, right? So we can see it. All right. 21 is not equal to the sum of x squared. Well, what was the sum of the x column squared? 7 squared. All right, let's go into paragraph to make this All right. So, yeah, so 21 is not equal to 7 squared, right? And I'm doing this with you, so it's not clean of errors. Like I'm just doing it, ignore the format as I work through it. So 21 is not equal to 49, right? So does that prove the rules? All right. So again, let's go back up. Before I move to the next piece, I want to make sure that the rules are indeed clear, right? So rule 1 says the sum of the x plus y column, which was 18, is equal to sum of x column plus y, 7 plus 11. So that balanced. The negative column is sum of the x minus y column, -4 is equal to 7 minus 11, which balanced. And then the other two did not balance. So now let's go back to our rule set, right? So here we are going to continue. Now I'm going to use the same numbers. Obviously, if we want to prove the rules, we probably should use the same numbers. So it was 2, 7, 4, 3, 1, 1, right? So, all right, let's turn this to 12. 2, 7, 4, 3, 1, 1. Now, I said in the video that K is a constant. So what we're going to do is we're just going to keep a very low constant. We're going to make our constant 2, right? So we're constant is 2, so we're going to put that everywhere, right? Now I'm going to do x plus k, right? So 2 plus 2 is 4. 4 plus 2 is 6. 1 plus 2 is 3. Okay, that column is done. Then we're going to go x minus k. So x minus k, 2 minus 2 is 0. 4 minus 2 is 2. And 1 minus 2 is -1. All right. And then kx. So kx, it's multiplying across. 2 times 2 would be 4. 4 times 2 is 8. And then 1 times 2 is 2. All right. And now I think I'm ready to add these columns and start proving these rules. All right. So adding the columns again, we're going to get the same outcomes, right? So for the first 2 columns, right? So 2 plus 4 plus 1 is 7. 7 plus 3 plus 1 is 11, right? So those were the same numbers above for the same x and y columns. K column, we have 2 plus 2 plus 2 is 6. X plus k is 13, right? 4 plus 6 plus 3. X minus k is 1. And then k times x column, we have 14. All right, so I've added these columns. Now I have to prove these rules the same way I did before. Right, so same rules apply as before. I'm just going to try and balance equations, right? So the sum of k column. Well, what was the sum of the k column? If we go down, is 6 is equal to n. Well, n is the number of participants. 1, 2, 3. Right. So really, when you think about this, you know what I'm going to do? I'm going to, right, I'm going to do tab. I'm going to just move it over and just label it as participants so you can see. All right. Participant, it's not working. I should have done it. All right. We're going to do it first with participant 1, right? So so I just labeled them number of participants. But the trick is just count down the column and see how many you have. So in this case, I have 3 participants, right? So n of 3 times the k, what was the k constant? 2, right? So let's see if that rule balances. 6 equals 3 times 2 is 6, right? So that rule does balance indeed. So now we're going to go to rule 6, which was the sum of the x plus k column, which was 13, is equal to the sum of x column plus the sum of k column is equal to 7 plus 6, which is equal to 7 plus the n times the constant. So rule 6 is pretty straightforward, right? So we took the x plus k column, we got 13. We match it with is equal to the sum of x plus the sum of k. So the sum of x column was 7, sum of k column was 6, and then n was 3, and then k is 2, right? So that's how these numbers got here. So we're gonna continue to move across. We're gonna say 13 is equal to, what's 7 plus 6? 13, great. And this should have had a plus sign to match the rule, right? Which is equal to 7 plus 6. And I like to work through until I get the same number through and through. So 13 is equal to 13 is equal to 13. Now all these rules are now balanced, right? So now we're going to do rule 7, right? Now I want to check this. Give me 1 second to see if I didn't copy rule 7 incorrectly. So I'm going to actually pause the recording and double check that. Okay, so I was correct. I knew that it looked off. I wrote the same rule twice, so I fixed that. And now we're going to work off of this rule. So the sum of the x minus k column, which is 1, is equal to the sum of the x column, which we said was 7, minus n minus k. We had 3 participants, that's n times k is 2. All right, so we're saying 1 is equal to 7 minus 3 times 2. So 1 is equal to 7 minus 6. Now, notice that PEMDAS is at play, right? Because I'm multiplying before subtracting, right? So I did 3 times 2 before the actual other work. So 1 is equal to 7 minus 6. So 1 is equal to 1. Last but not least, KX column. KX column, we got 14, right? So, okay, KX, we got 14 is equal to K, which was our constant, 2, times, right, because anytime there are letters next to each other, we multiply the sum of the x column, which is 7, right? So 14 does indeed equal 14. Now, look, I proved all the rules, and it's a lot easier when I can write on the board and have you come up. But I think for our purposes, getting through the pandemic and still trying to teach the rules, create these columns on the fly, and then show how the rules actually work. Um, we did a fairly good job. So I'm going to stop there, and that is our first lesson.